as Henrik said, the effort, and then there will be a couple of other talks following mine to discuss a bit more details. ICID is the acronym we use, but then really this description is the coordinated measurements at high Reynolds number, zero pressure gradient boundary layers in 3 different tunnels. There were 4 main groups, many participants. In fact, some of the groups had participants from other universities. So, for example, Beverly, who's here and who's declared was part of this group, Alessandro and Danielle and Suji and his colleagues were in KPH group. So, with that in mind, let me tell you what the scope is of the effort. Zero pressure gradient, boundary layers, high Reynolds number. There were some comparisons between facilities and so forth, but ultimately we wanted a range which is sufficiently large, as I will show you. This was the range of speeds from 10 to 60 meters per second, from 5.5 to 22 meters in terms of the X for developing the boundary layer, and the Reynolds numbers were basically in this range. This is the key to all of this, which will be discussed in the following talk by John Danielle. This is an independent measurement of the wall shear stress. And as I said before, if you don't have that independent measurements, the value of your other measurements have very limited use as far as we can see. Compare the high Reynolds number, zero pressure gradient boundary layer. Establish reliable estimates of the accuracy and repeatability of oil film. If you read in the literature, you see numbers that will be improved upon a great deal when John Danielle talks about his accuracy estimate. This is something that already Ivan talked about, so I will skip it because he's highlighted some of the issues. We were interested in making comparisons between hot wires and Peter. In fact, that's how the whole effort got started, in a conversation between me, Beverly, and Lex in some Canadian town some long time ago. And we wanted to find out if some of the differences are real and what they are, and in terms of other overlap parameters. 3 facilities, and for those of you that were here last week, I kind of gave advertisement for some of this. This is the MTL tunnel. Most of you have seen it here. The dimensions of it will grow a little bit as we go to the other 2 tunnels. The speed range will go down from this tunnel as we go to Melbourne, or will go up in NDF. The NDF is a larger test section. This is a suspended flat plate. So is the NDF, but as Ivan pointed out, the Melbourne tunnel, the boundary layer is developed on the flow. So as the flow comes out of the contraction, it just tripping was used in all the facilities, and that's a subject of much longer discussion. The pressure gradient is adjusted here by small amounts, flexibility changes of the configuration of the surface. In Melbourne, it is basically the pressure gradient between the test section and the outside with a fixed venting. In the question period, if we have time, I'll just say something about that, and I said something about it last Friday, but let me not spend any time on it. The MDF has far more flexibility in terms of the adjustments of the seating and the test section, but it's in many ways the MTL and the NDF are geometrically very similar. So that's, but the NDF is a bit bigger. With that in mind, if you take a look through the literature and you plot versus RE delta star, I know people like RE theta, but we from a theoretical point of view, RE delta star is a much more robust because of the correct length scale being delta star and the theory, and the Rota-Clauser scale. The points you see here is the typical measurements, including some of the NDF older data. and so forth. This is the NDW work, Fernholz and co-worker. The range of the isotope measurements is here. In RE delta star, you basically need to get to here before you get to what we call high Reynolds number. Okay? So this converts between the values I'm giving here and what the blue line. And the blue line is actually a fit based on the work that we did with Charles Allen. And you will see Backham again and Charles Allen will show. It's based on the log line, asymptotics of the log line. In fact, the light blue line is a low Reynolds number correction of it that Kapil Chauhan had developed. I want to spend a few minutes because if this effort taught us something, the Achilles heel of all of these hot water measurements, high Reynolds number measurements, is basically the accuracy of your measurements of how far you are from the wall. And it turns out, and I'll tell you how hard it is, all the groups work on this, ultimately you need to rely on some kind of theory, DNS, or some other tool to support your corrections. It's very small because I don't give you the challenge. Some of the experiments, this happens to be the experiments by the Melbourne and the IIT groups in the NDF. The traversing mechanism carried two probes simultaneously. One was a smaller sensor, so one was measuring the RMSs and so forth, and one was measuring the mean because of the drift issues that Ivan said about. So as hard as you make the measurement to the wall, as I would point out, you also have issues with deflection of the traversing mechanism as it traverses out. You have issues of a deflection of other things, and so that is a big challenge. I'm going to talk about this later on, but Henrik will point out several techniques that were used to establish what is the true Y plus. I will tell you how the original Y pluses were made, but there are several techniques here that have been used by the different groups and the comparisons. I don't have the time to discuss them, but one of them I use as a sample here. The initial measurements here, and I'll take an example of the Princeton probe actually in the NDF. You use very accurate optics and electrical techniques and so forth to measure the initial distance. And quite often you measure it with very accurate measurements. The point is, once you finish doing this, you have to close the wind tunnel when you start the flow. In fact, that value is no longer exactly the same. Okay? Because we're not talking about big numbers, we're talking about microns. So it's very, very different. And then as the probe traverses, and we're taking data, it's also that reference value is not exactly the same. And this is true from all the measurements. Okay, so I pointed it out here, and in effect, so you have the file of measurements and read. So sometimes the correction involves values of like 1Y plus or 2Y plus correction, which in some of these high Reynolds numbers are extremely small values. Yes?
Which are the dimensions of the object you are showing us?
The actual physical dimensions?
Yeah, the length.
Beverly, actually, I'll show you the diameters of these probes. I think, Dr. Beverly, this is...
No, I was thinking of the main structure of the big thing.
Well, let me tell you, I'm focused in this photograph on something here. So you have the supports and so forth, and usually measuring far upstream, not to disturb them.
But then the vibrational or the structural problem that you are mentioning, is this related to the main structure or just to the small?
Both.
Because the largest vibration you should get by optical interferometry.
We have, for example, in many of these measurements, the probe as it was traversed was followed by a camera, a high-resolution camera over.
But why not putting a sort of a diode or something that shoot light and then...
Let's talk about that separately, because otherwise I will miss making other point. So, 3 facilities, the velocities involved, the locations. In KTH, all of the measurements were at 1 location, now we're in 3 locations, and we have 2 locations. But you can see the Reynolds number range in RE theta. And you can see the things that have the same color, saying that in different facilities we match the same Reynolds. Okay? Now, here's a comparison by the Princeton probes in actually 2 facilities. The data, this was a slide that I got from Sean Bailey, but you can see with the corrections of the theta probe for the velocity gradient effects, you can use theta probes over a wide range, and that collapses extremely well, so we feel very comfortable about that part of which is basically contained in the work that Beverly and Lex have published in the past. This is a comparison between the 2 facilities. You can put the third one, I just didn't have the slide prepared, and it looks the same with the same probes because they came to IIT, the probes came to IIT. And this is the measurements at different Reynolds numbers. So things look quite good here. In hot wires, I can show you that in the inner scaling, the collapse of the data from 4 of them, from the various tunnels in the mean look good. I'm going to focus on a part coming up. The outer scaling, and I'll come back to this, of the same velocity profiles. This is data by different people, different facilities, different time of the year, different continents. But now, let's start looking at some characteristics of this data. For example, you can calculate the integral parameters. We've also fitted the composite profile, which I've talked about before. And out of that, you can make estimates of pi and so forth. It turns out pi is extremely sensitive parameter. If you take a look at the shape factor as a function of RE delta star, this is the relation that we published recently with plus or minus 1%. The data from the various experiments cluster very well. This is extremely enlarged scale. If you go to pi, pi is a bit tricky. You have to be very careful. This is the similar asymptotic relation we derived. The data actually settles to this Reynolds number. The kind of collapse that has been reported in the literature by Coles and others, we don't see. In fact, I think it's a manifestation of problems with fitting the profile, the log-log estimates of kappa, and other things. Here is the first interesting results, which I will show you. The initial estimates of kappa using this approach consistently clusters around 0.38 from all of the measurements, with the exception of those obtained by the pedal probes. Okay? So this is already a difference. I mean, we're talking about small differences, but it's about a difference of 0.01 or so. And this is, in a way, was what Beverly, Lex, and I started thinking about. Before I explain that quickly, let me tell you that there are ways to check the consistency of these results. Fitting these curves I showed earlier, one should not do arbitrarily. The slope here, the slope in the previous figure, and so forth have to all be consistent. You can do that by looking at the outer fit, the inner fit, the skin friction relation, and these constants have to be consistent with each other. If they don't add up in the asymptotic limit, something is wrong. And we've talked about this in some publication. Actually, the reference, I believe, is down there. And here is Rich Duncan's calculations of A's, B's, and C's. Remember, the C you get from the skin friction curve that John Daniel will show you. It's a completely different oil film measurement. The A's and the B's you get from the hot wire fit, and they better add up to each other. Okay? And you can see how well the data is. Now let me go back and take a couple of minutes and focus on what people talk about as a turbulent convection to picopros. This is a curve I showed you earlier, but I singled out only the hot wire data in Melbourne in the same facility with the Princeton data at Melbourne. And it looks quite good here, but let me focus zone on this part. And I'm not saying the log part. I'm focusing. This is all zero pressure gradient boundary layers.
And
There are symbols here in green that are hot wire, and in this brownish color is heat. Okay? So now I focus on this zone. The same two codes in color. Actually, there is some blue data which is also hot wire. You can see there is a difference here between those two sets, between 10 and 100. Not in the log law. Remember, the log law starts around 200 or so. And that difference is correctable with very simple turbulence intensities. In fact, I'll show you the correction. I say here, this is preliminary, and even amongst the various ISID groups there are different views. So this is my current interpretation of things, but we can discuss that.
And skin friction was measured the same.
Skin friction is determined by the oil film, and once you get that U tau in that Reynolds number, you don't touch it anymore. This correction was done both by Rich Duncan and by Jason Monty. This happens to be Jason Monty's slide, using very simple corrections to the turbulence intensity. Now, this correction in that zone actually leads to a difference in estimating kappa by this much. Okay? It is basically, and I'll show it to you so about a 0.01 difference. Just this is uncorrected for turbulence, this is corrected.
That's why you weren't looking at the log region, so how are you getting kappa?
Because it is using the composite fit to do the whole profile. Because we can go, so as I said, we do this, all these kappas were done using the same composite fit. Okay? Now, here's a different way of doing it by Jason. On Jason, uncorrected, corrected. Now, semi-corrected means it isn't, but let me plot it this way. So, uncorrected is here. This is corrected only for the mean without the turbulence intensity. This is all pitot probes. Now, this is all the pitot probes corrected as I just showed you, and the hot wire. This is basically delta U plus, which is the difference between that value and the reference value. You can do this also with the indicator function, which is the derivative. Now, what happens is if you correct it, or you take the difference between them, you notice that the difference between them concentrates where the turbulence intensity is high, namely between 10 and 100. So
which do you think is the correct sort of scale in your mind? I don't know.
well, I mean, as I think there is a slide here from Jason says, first of all, that's a separate question, is which is really more accurate, okay? But the point is we're highlighting the fact that if one accepts the pressure measurements of pitot probes are influenced in the high turbulence level region by turbulence in addition to other effects, and just simply corrects for them, it brings the two together.
Not really collapse on each other.
Virtually collapse on each other. In fact, I think I forgot to add one slide from Jason. I apologize. If you make that correction, this curve drops on this curve. Okay? Just the same way I showed it earlier, this is Rich's values of it. Here's without the correction, watch what happens to the yellow points, and this is with the correction in the same region.
Also, Pitot only measures the total pressure.
The pitot is measuring only the total pressure. The static pressure in all of these measurements were at the wall using the criteria established by Beverly. So there was no error from measuring the static pressure at the wall.
You will then correct for the changes in static pressure as you go across the boundary.
That's
You get the Rome's wave term.
No. No.
So that effect is even larger than the use wave effect.
Not in these boundary layers. I don't think so. But we should talk about that. Let me first close so that Henry can. And I'm just showing you some of the pictures of the people that participate in these experiments. Thanks, Henry.
Okay, thank you very much, Hassan.
ISET measurements. I will be a few talks around that see now. Question for us has to do for later, but now the most important talk I think that Hassan says, and I think I agree with it, is really the independent measurement of the water stress. And